Hello students. So welcome to one more video. Today in this video we are going to discuss about one more topic from class 12. That topic is Kirchhoff's laws. Okay. Now those who are doing current electricity, I hope all of you are well aware with this topic. Now if you are doing circuit diagrams, okay, so that is numericals involving circuit diagrams. So the first thing that you have to know before doing the circuit numericals based on circuit diagram is Kirchhoff's law. Okay, so some students might find it little bit confusing, but in this video I shall explain to you in the easiest way possible. Okay, so let's start. Now, Kirchhoff was a scientist. His full name was Gustav Robert Kirchhoff. Okay, so Gustav Robert Kirchhoff. Now, in the year of 1842, okay, in the year of 1842, he gave two laws, okay, and these two laws made our calculations based on current electricity very simple. Suppose we have a very complicated circuit. How to solve that complicated circuit? How to find out the currents in each branch in a very easy way? So that path was led by this famous person Kirchhoff. He gave two laws, and those two laws are known as the fundamental laws of solving the numericals, some certain complex numericals based on current electricity. Okay, so let us see what are those two laws. So the number one, the first one, okay, the first one is known as Kirchhoff's first law. Kirchhoff's first law or junction rule. Junction rule. Okay, or you can say the current law. Current law. In some of the books, it is also written in short form as KCL. Kirchhoff's current law. Okay, Kirchhoff's current law. So this is the first law that he gave us. It is known as Kirchhoff's first law, or you can say junction rule, or you can say current law, or in short KCL. Okay, what does this law states? Now, this law states that, look, in an electric circuit, okay, in an electric circuit, let's first see the law, what the law tells us. In an electric circuit, the algebraic sum, okay, the algebraic sum of the currents, this one also you can say net current, okay, also you can say net current. Algebraic sum of the currents meeting at any point, okay, so the algebraic sum of currents meeting at any point or any junction is always zero. Okay, this law is also written in this as summation I equals to 0 or summation I net equals to 0. Or you can say only write summation I. Okay. Now what does this law mean? Okay. Now see, when you are solving any complex circuit, okay, if you are solving any complex circuit, in many places you will get junctions. Now what is the meaning of that junction? Junction means a point in the circuit where many wires assemble. That means many wires are either coming out from that particular point or going to that particular point. Okay, it's a point from where many wires are coming out. Okay, that particular point is known as junction. Okay, so in a particular circuit there can be many junctions. Suppose if I draw any circuit like this. So this is a circuit. Okay, so this is a circuit, a very basic circuit I am drawing with three resistors. Okay, and this is a cell and this is a switch. Fine. So these are the three resistors. Okay, now see, let's first understand what is the meaning of junction. You see, this terminal, this particular point can be named as a junction. Okay, or this particular point can be named as a junction. You see, from at this particular point, this wire is coming out, this wire is going, this wire is going, and this wire is also going. Okay, so this is a junction, this is a junction. These are known as junctions in a particular circuit. Fine. Okay. Now, Kirchhoff's law states that if you get any junction, in that particular junction, current might go into that junction or current might come out of that junction. For example, if I show you this circuit, this is a cell. Suppose current I is flowing through here. So that from the battery. These are the three resistances R1, R2 and R3. So current I is flowing into this junction. Okay, current I is flowing into this junction, and from this junction, suppose I1, I2 and I3. These three currents are flowing out of this junction. So if you take any junction, any circuit, so current might enter that junction or current might go out from that junction. Okay, so these two things can happen. So let this be clear at first. Now Kirchhoff says that if you get any junction, suppose we have a junction over here, we have a junction over here, okay, and these are the wires coming out from the junction. So these are the wires coming out from the junction. These are the wires coming out from the junction. Suppose I1, I2. Suppose I3 is going out, okay, I3 is going out, suppose I4 is going out, I5 is going out, I6 is coming. So I1, I2, I6, these three currents are flowing into the junction, and I3, I4, I5, these three currents are flowing out of the junction. Okay, so if you get any junctions, current might flow into that junction or current might flow out of that junction. But this law is very simple. Kirchhoff says that at any junction, if you take any junction, the algebraic sum of the currents or the net current must be always equal to 0. Now, what is the meaning of algebraic sum? Algebraic sum means if current is entering the junction, if current is entering the junction, okay, we take that current to be positive. So if current is entering the junction, we take that current as positive. If current is flowing out, current is flowing out of the junction, we take the current to be negative. Okay. So if current is flowing into the junction, we take, first you have to understand the sign convention. So what sign convention? Sign conventions can be different for different users, so no problem in that. Okay, I am telling you the sign convention which is given in most of the books. So this sign convention is, if current is flowing into the junction, then that current we take it with positive sign. Fine. If current moves out of the junction, then that current we take it with negative sign. Fine. Okay. Now, suppose this junction is O. You see this I1, I2 and I6, these three currents are flowing into the junction, so we will take it with positive sign. I3, I4 and I5, these three currents are coming out of the junction, so we are going to take it with negative sign. And then if we do the algebraic sum, then that algebraic sum must give us 0. Okay, that means in this particular junction, if you see, so I1 plus I2, so these are the plus signs, okay, I1, I2, I3 is coming out, so minus I3, I4 is coming out, so minus I4, I5 is coming out, so minus I5, I6 is coming inside, so plus I6, must give us 0, okay, must give us 0. So this is Kirchhoff's first law of the junction rule. Fine. Or you can write I1 plus I2 plus I6 equals to I3 plus I4 plus I5. Okay, so this is Kirchhoff's junction rule. So it basically says that whatever current will come inside the junction, that much current must flow out of the junction. Okay, that means the incoming current must be equal to the outgoing current, total current. Okay, so incoming currents must be equal to the outgoing current. So whatever current will come into the junction, that much current must flow out of the junction. Okay, so this was basically Kirchhoff's first law. Now, one very important thing, Kirchhoff's first law basically tells us about the conservation of charge. Conservation of charge. Now, what is the meaning of conservation of charge? Conservation of charge means same thing like conservation of energy. That means charge is not created or charge cannot be stored in any place. Okay, stored means if you see this particular junction, you see Kirchhoff says that whatever current will come into a junction, that much current will flow out of that junction. Fine. Now let us assume that Kirchhoff's law is wrong. It is not wrong, but let us assume for a second that if Kirchhoff's first law is wrong, it means that the total current which is coming into this junction, suppose it is not equal to the current which is moving out of the junction. If Kirchhoff's law is wrong, for this law is wrong, then it will mean that the total current which is coming into this junction, that much current is not flowing out of the junction. If this is the case, then at this particular point, there will be an accumulation of charge. Okay, there will be an accumulation of charge. There will be an accumulation of charge. So if the incoming current is not equal to the outgoing current, suppose let us assume that the incoming current is more, okay, and the outgoing current is less. Okay, so if this process is continuously happening, so what is going to happen at that particular junction? Charge is going to accumulate continuously, and we know that thing can never happen. Okay, because whenever current is flowing through any conductor, we cannot store the charge at one place. Charge has to flow through the conductor, otherwise the circuit will stop working. Okay, otherwise the circuit is going to stop working. So that's why accumulation of charge is not possible. Accumulation of charge at any junction is not possible. So if I look at any junction, whatever charge will come into that junction, that much charge must flow out of that junction. It has to happen. Okay. Also, if you think in the opposite way, suppose the outgoing current is more. Okay. Suppose if you think that the incoming current is less and the outgoing current is more. Now you see that is also practically impossible. From where is that extra charge coming? Because we know that at this particular junction, only these 6 wires are there. Okay, so whatever has to happen, this 6 wires is going to do. Okay, whatever task is going to happen, this 6 wires are only going to do. So suppose if the outgoing current is more than the incoming current, then that extra charge from where it is coming. So that is practically not possible. So basically this law tells us about the conservation of charge. Okay, so that was Kirchhoff's junction rule. This is a very helpful rule, okay, when we are solving numericals based on very complicated circuits. Okay, in that particular case, we can easily use this Kirchhoff junction rule to sort out or make the circuit simpler. Okay, so once you understood this one, we can go to the second rule, Kirchhoff's second law. Okay, so let's see Kirchhoff's second rule. Number 2, Kirchhoff's second law. So Kirchhoff's second law is also known as the loop rule. Loop rule. Like the previous one was known as the junction rule, this one is known as the loop rule. Fine? Or the voltage law. In some places, it is also written in short in KVL, Kirchhoff's voltage law. This particular law is much more important than the first law. Remember, students, this particular law is much more important than the first law, and this is a little bit complicated also, not so much complicated. You just have to remember 2 to 3 things before applying this law in any electric circuit. First, let us see what this law tells us. Okay. So Kirchhoff's law tells that the algebraic sum okay, of all the potential differences okay, about any closed loop okay, about or around any closed loop is always 0. Okay. See. Now Kirchhoff's first law basically tells us about a current. Okay, this law tells us about the potential difference. Right. So it states that the algebraic sum, again you see algebraic sum. So once you hear the word algebraic sum, you have to just put it in mind that there have to be certain sign conventions that you have to understand. So here also there are certain sign conventions. It says that the algebraic sum of all the potential differences, okay, about any closed loop. This is very important word here, loop. Okay, closed loop. So the first law was about junction. This law is about loop, right? Is always 0. Fine. So let us first understand this law. But to understand this law, you have to remember first 4 certain things. 4 things. Now first I am going to draw a very simple circuit to you, and as we will solve the circuit, I am going to explain the laws to you. Okay. So a very simple circuit I am going to show you. Suppose this is a circuit. Here I am connecting a cell. Suppose the EMF of the cell is E1, right? Here I am connecting a resistance R1. Okay. Here I am connecting one more cell. Here I am connecting one more cell, and here I am connecting one more resistance. This is R2. And over here I am connecting one more resistance, R3. This is E2. Fine. Okay. Now see, normally if you want to solve this particular circuit, okay, if you want to solve this particular circuit, it will be very difficult for you, because you see there are 2 cells over here with different EMFs. Okay, there are 2 cells with different EMFs, and you will not understand whether you have to connect these 3 resistances in series or parallel. This is nothing, neither series nor parallel. So what you are going to do? Over here, Kirchhoff's law comes to our help. Kirchhoff's law helps us to very easily identify this or make this circuit very much simpler. Okay. One more thing Kirchhoff's law helps us to do, that is to find out the currents in each branch. Okay. Let's first see, once current is going to flow in this circuit, how it is going to look. So suppose, let's see from here. From this particular cell, current I1 is coming out. Okay. From this particular cell, current I1 is coming out. So I1 will flow through this way. I1 is going to flow through this way. From this particular cell also a current will flow. Suppose I2 current is flowing. Okay. I2 current is flowing. So I2 will flow over here. Now when I2 will come over here, it is not going to go up, because here there is a positive terminal. Okay. And I1 will also not come over here, because here there is a positive terminal. So I1 is going to come down, as well as I2 is also going to come down. So in this branch we are going to get I1 plus I2. Now that I1 plus I2 is going to flow through here. I1 plus I2. So this resistance. Okay. So through this branch also I1 plus I2. Okay. Now over here through this branch current I2 was flowing, so I2 will enter over here and I1 will go along its own path. So from here I1 will go. So this is how current is going to flow in this particular circuit. Okay. Now you have to find out, the question is you have to find out the currents in each branch or current I1, I2. Once you find out current I1, I2, you can just, if you want to find out the current in this branch, you can easily add I1 and I2. Okay, so the task is to find out the current I1 and I2. Now, this will be very difficult if you want to solve it in a normal procedure, in a normal way, because resistances you will not be able to understand whether to take it in series or parallel. Okay, so over here Kirchhoff's law comes to our help. Okay, Kirchhoff's second law. Now see how to solve. Okay. Kirchhoff's law states that the change in potential across any closed loop is always zero. The algebraic sum of the changes in potential across any closed loop is always zero. Now, what is a closed loop? First, you have to understand. You see, in this particular circuit, you can see this one is one particular loop. Okay, you see, this is one loop. This is one loop. Loop means in a particular circuit, a closed particular area. It has to be a closed area from all the sides. Okay, that is known as a loop. You see over here, this is a loop. Okay, and again, this is one more loop. Fine. So first, what you have to do in the circuit, you have to identify the loops. How many loops you are taking. Now this one also can be a loop. The entire circuit, this full thing. Okay, if you remove this one, this thing also can be a loop. But over here, for in this case, our two loops is enough. You have to understand how many loops you need to take. Fine. So now, at the end of this portion, I will tell you how many loops, how to understand how that means how many loops you need to take. For now, you can just take two loops. This is one particular loop. This is one particular loop. Now you see, in this particular loop, over here there is a potential difference E1. Right? Over here also there will be a potential difference. Now current I1 is flowing, resistance is R1. So what is the potential difference? I1 into R1. Here there is a potential difference. Here also there is a potential difference. Here also there is a potential difference. So Kirchhoff's law states that the algebraic sum of all the potential difference across a closed loop is zero. The algebraic sum of the potential difference across any closed loop is always zero. Now what is the meaning of this one? He says that the algebraic sum of the potential, this potential difference plus this potential difference plus this one, if you are taking this loop, okay, if you are taking this loop, then this potential difference plus this potential difference plus this potential difference will give you zero always. But the thing is, the most important thing is, it has to be algebraic sum. So algebraic sum. So how to understand which potential difference to take positive and which potential difference to take negative. Okay, for this you have to understand four things. Now in different books, different things are given. It is given in a different way, but whatever is given in most of the books, I am telling you that one in a very simple way. Fine. Number one, here I am writing. You see, number one. Now, once you have taken the loop, you see, once you have taken the loop, the next thing, the first thing is you have to identify the loop. Okay, these are the three things you have to do. First thing is identify the loops. You see how many loops you need to take. So first thing is identify the loops, name the loops. Here I have named the loop 1 and loop 2. Okay. Next, what you have to do, the second thing is you have to start from any point. Okay, start from any point in the loop and you have to go through the entire loop. You have to go through the entire loop. Okay, and again end at your starting point. Suppose in this particular loop, if I start from here and if I decide that I am going to go in this direction. Okay, so I have to go in this direction, and again I have to come back over here. But the condition is, there is a condition. Condition is whichever, you can choose any direction. Either I can choose anti-clockwise direction or I can choose clockwise direction. It is my choice. It is my wish. Any direction you can choose, the answer will come same. Okay, but there is one condition. In the midway, you cannot change your direction. Remember this, students. Okay, this is a particular region where many students I have seen they make mistake. in midway they change their direction. Okay, they get confused and change their direction. Remember this, once you have chosen your path and you start from here and you are going through here, suppose when you come over here, you cannot again go back in this direction. You have to complete your path in the same direction, okay, irrespective of the direction of the current. Do not get confused by seeing the direction of current, okay. It's your path, and you have to choose in which direction you have to go. Okay, suppose I am telling I will go in this direction, okay. This one, suppose I am going in this direction. Any direction you want, you can go, no problem. Okay, remember your starting point from where you are starting. Okay, so the first thing is, if you are going down the current. Now, what is the meaning of down the current? Down the current means if you are going in the direction of the current. Suppose while going in your direction, you are going in you have to follow your path, whatever path you have taken. So in your path, suppose if you find anywhere, okay, where you see that the direction in which you are going, in that direction only current is going. Okay, you might think, suppose you have chosen a direction. This is the direction that you have taken. So the condition is you cannot change your direction midway. Now suppose in your entire journey you will get many ways. Suppose from here if I start, I will get this word, then I will get this word, then I will get this word, then I will get this word. These 4 words I will get. Okay, so in your entire journey you are going to get many words. Fine. Some of the words you may see that current is flowing in your direction. In some of the words you may see current is flowing in the opposite direction. It doesn't matter. You have to complete your journey in the direction which you have chosen. Fine. So if you are going down the current, okay, that means if you see that the current is flowing in your direction. If you see that current is flowing in your direction, then that potential difference you will take as negative. Okay, that particular potential difference will be with negative sign. Fine. If you see that you are going up the current means, suppose in your loop you see that suppose you are going in this direction, you cannot change your direction. Suppose you are going in this direction and you are seeing that current is flowing in the opposite direction. You may find that sort of way also. Okay, current is always not going to flow in your direction, because current is going to flow according to battery. You are going to flow, that means you are going to move according to the direction which you have chosen. You have no relation with current. Current is going to flow according to the battery, how the circuit is designed. Okay, and your path you have chosen. Do not get confused by seeing the direction of current. Okay, put this in your head. Okay, very nicely. Do not get confused by seeing the direction of current. Fine. You may see in certain regions that current is flowing in your way. You may see in certain regions that current is flowing in the opposite way. Doesn't matter. Everything will be adjusted. Just use the correct sign. Okay. So anywhere if you are seeing that you are going in this direction, current is flowing in the opposite direction. That is known as up the current. Okay, or current is flowing in the opposite direction. So current is flowing in the opposite direction. In that case, we will take the potential difference to be positive. Okay, in that case, we will take the potential difference to be positive. Okay. Number 3. You see, these two are, if you are crossing any ray, we know that potential differences. When will there be any potential difference? If you cross in a resistor. Okay, if you cross in a resistor, then there will be potential difference between across two ends of the resistor. This is a copper wire. Through any copper wire, copper is a very good conductor. In my earlier videos, I have told you many times, copper is a very good conductor. So there is no potential drop across a copper wire. Fine. So through a copper wire, the potential remains the same. There is no potential difference. But through any resistance, across any resistance, there has to be a potential difference. Okay, so this is across any resistance. Okay, one more time, potential, there can be a potential differences when you are crossing a cell. You see, in your entire journey, you will get resistances and you will get cells also. So whenever you are crossing a resistance, there will be a potential difference. Also, when you are crossing any cell, there will be a potential difference. Because you see the EMF of the cell is E1, this cell. This is positive terminal, this is negative terminal. So this is higher potential, this is lower potential. So there will be a potential difference across a cell. Okay. Now see. In a cell, if you are going from the lower potential to the higher potential, okay, in a cell, if you are going from the lower potential to the higher potential, you see, that means if you are going in a cell, across a cell, here I am writing, across a cell, if you are going from the negative terminal to the positive terminal. So across a cell, if you are going from the negative terminal to the positive terminal, okay, if you are going from the negative terminal to the positive terminal, that means from the lower potential to the higher potential. So suppose in your journey you are seeing that, because as I said, you cannot change your direction, okay, you have to follow your own direction which you have chosen. So in your direction, if you see that first you are crossing the negative terminal, then you are crossing the positive terminal. That means you are going from your lower potential to higher potential. In that case, consider that potential difference or the EMF, okay, to be positive. Change EMF to be positive, okay. Opposite. While going across a cell from the positive terminal to the negative terminal, that means from higher potential to lower potential. So across a cell, if you are seeing that you are crossing the positive terminal first in your journey, okay, you are crossing the positive terminal first, then you are crossing the negative terminal, okay, so that EMF, take it with negative sign, okay. So these two rules will be while you are crossing any cell, okay, while you are crossing any cell. So remember these 4 points before starting, okay. Now when you know these 4 points, when we know the sign conventions, these are the sign conventions, okay. So once you know these sign conventions, we can start, okay. Fine. Remember students, so as I told you, you cannot change your direction, okay. Remember your starting point, okay. You see. So first we are going to take loop. So suppose we are taking loop 1. We are taking loop 1, okay. Loop 1 we are taking, fine. Now suppose this is your starting point. This is your starting point, okay. Now first, when you get in certain numericals in the question, the distribution of current is already given, okay. So if the distribution of current is given, so your one work is already done, okay. So your one work is already done, you don't have to do that one. But if the distribution of current is not given, then the first thing that you have to do is mark the currents. Second thing that you have to do, remember the steps. Second thing that you have to do, mark the loops and see how much loop you require, how many loops you require. Mark the loops. Third thing that you have to do is mark the direction in which you want to go, not the direction in which current is flowing, the direction in which you want to go, you want to follow. Mark that direction. Fine? Okay. Now let's see. So suppose I will start from here. As I said, I will go in this direction, in the anti-clockwise direction. Okay. So the first potential difference I will face is this one. Okay. Current I1 is flowing, resistance is R1. So what is the potential difference? I1 into R1. Now see, we are going down the current. You see, because my direction is in that direction only, here over here current is flowing. So down the current, potential difference will be negative. Okay. So I will write minus I1 R1. Fine. Now see, the next potential difference that we are going to face is this one, E1. Okay, E1 is the EMF of the cell, E1, right? So see, we are crossing the negative term because I am going in this direction. In this direction I am going, okay. So we are crossing the negative terminal first, then the positive terminal. So from negative to positive we are going. So EMF we will take it with plus. So plus E1. Okay. Now from here we are coming, this is a copper wire, no changes in potential here are coming. Again over here you see, again over here we are getting one more cell. But now you see we are crossing the positive terminal first, then we are going to the negative terminal. So first we are crossing from positive to negative. So EMF we will be taking with minus sign. Okay, so this is minus into. Okay, let's follow our path. Let's follow our path. Do not change your path. Do not change your direction. Okay, repeatedly I am saying the direction in which you have chosen. Do not change that direction. So once again over here you are going to get one more potential difference. You see through this circuit, through this resistance, current I2 is flowing and the resistance is R2. Okay, current I2 is flowing and the resistance is R2. Fine. Okay. So what is the potential difference? I2 into R2. I2 into R2. I2 into R2 is the potential difference. But you see, I am moving in this direction. I am moving in this direction. But here current is moving in the opposite direction. Right? Do not get confused. Get confused by the direction of current. Do not change your direction. I will still be moving in this direction, but now I am seeing current is moving in the opposite direction. So you are going up the current. So if you are going up the current, then potential difference will be plus sign. So potential difference will be plus I2 into R2. So there are no more, so just complete your path up to here. So there are no more potential differences across this path. No more potential difference. So Kirchhoff says that the algebraic sum of all the potential difference will be equals to 0. This is your equation 1. Okay, this is your equation 1. Let us take loop number 2. Loop 2. Loop 2. So loop 2 is this one. Here I have decided that I will go in this direction. This is my wish, I will go in this direction. If you want, you can go in the opposite direction also, no problem. Okay. Now see, in this loop 2 is this one. Now, if you are thinking that this particular branch you have already taken and now you cannot take, that is wrong. This particular branch belongs to this loop also and this particular branch belongs to this loop also. So when you are doing for this loop, once again you have to take this branch, okay, and once again you have to follow this procedure, okay. So from any direction you can start. Suppose I will be starting from here, okay, I will be starting from here. So from here I am going, so in this direction I am going, okay. Now over here you see this is the first potential difference that I will face. This is E2. We are crossing the positive, then we are crossing the negative, okay. First you are crossing the positive, then negative. So EMF will be with negative sign. So minus E2. Then we are going, okay. Here again, there will be potential difference. I2 into R2. I2 into R2 will be the potential difference. Fine. Now see, let us see, we are going up the current or down the current. Current is flowing in this direction. Current is flowing in this direction. I am going in this direction. So I am going up the current. Up the current means positive sign. So plus I2 into R2. Plus I2 into R2. Right. Then again we are coming from here, we are going through here, okay. Over here also, we will be getting one more potential. Current is I1 plus I2, resistance is R3. So the potential difference will be I1 plus I2 into R3. Over here you see current is flowing in this direction. Current is flowing in this direction, I am going in this direction. So again I am going up the current, so that means positive. So plus I1 plus I2 into R3, okay, and no more potential differences, so I can complete my path. So my path is complete, okay. So again Kirchhoff says that the resultant will be equals to 0. Okay. Now once you have taken out these two equations, now what? Now what you will do? Now see, if you know the value of the resistances and if you know the value of the EMFs, okay, then if you solve these two equations, by solving these two equations, simultaneous equation, by solving you can get the values of I1 and I2. You can get the values of I1 and I2 because you see two unknowns, two equations, okay. Now in just few minutes back I told you how you will understand how many loops to take. Just see how many currents you need to find out. Over here, there were only two unknown currents, but there might be certain complicated circuits where there are 3 or 4 currents, I2, I3, I4. Okay, I2, I3, I4. So 3 or 4 currents might be there. So if you have 3 unknown, then we need 3 equations. If you have 2 unknown, then we need 2 equations. Over here we had 2 unknown, so only 2 loops were enough. 2 equations were enough. But if we have one more current, then we need one more loop to solve. Okay, one more equation to solve. That is how you will understand how many loops you have to take. Take the minimum loops as possible, number of loops as possible. Okay, so if you solve these two, you will get the values of I1 and I2. So this was all about Kirchhoff's voltage law. This law is much more important than the first law. Okay, this law basically tells us about the conservation of energy. Conservation of energy. Now, why this tells us about the conservation of energy? You see, potential difference. Okay, the formula for potential difference is work done per unit charge. This is the formula for potential difference. Okay, potential difference means work done per unit charge. That means whenever a charge is, suppose any electron or any charge, it is crossing a potential difference, it has to do a work. Okay, whenever any charge is crossing a potential difference, it has to do a work. So that's why potential difference is known as work done per unit charge. Okay, unit charge, how much work it is doing, that is known as the potential difference. Now, if this is false, okay, if the algebraic sum of the potential difference is not 0, okay, that means whatever potential differences we are taking with plus sign, that is not equal to the whatever potential difference we are taking with minus sign. Okay, if that is not true, then what is going to happen? Through anywhere, whenever charge is flowing, okay, whenever charge is flowing through any particular loop, constantly we are going to get energy out from that. We know practically that is not possible. Okay, practically that is not possible, because whenever current is flowing through any circuit, energy has to be conserved. Whatever will be the gain in energy, that must be also equal to the loss in energy. And potential energy is equal to, potential difference is equal to work done per unit charge. Work done is energy, how much energy it is spending. So whatever energy the charge is going to do, charge is going to gain, that much energy the charge has to lose also. Okay, if that is not true, then a charge continuously will increase its energy again and again and again. It will continuously go on increase its energy, and that will violate the law of conservation of energy. Okay, so this law basically tells us about the law of conservation of energy. Okay, I hope this particular topic is clear to you all. If you have any doubt, please let me know in the comment section below. I hope you like the video. If you like the video, please like and subscribe. Thank you.